To solve some problems of bit and its successor, we propose the shunted transformer. I'd like to show the performance at first before going to the details. We apply model on ImageNet-1K classification. The red one is our model and the green line represent previous state-of-the-art focal transformer and the yellow one represent the baseline model DEIT. Our model shows superiority cross different model size. For large model, our shunted transformer outperforms the state-of-the-art focal transformers, while having the model size. When scaling down to tiny sizes, shunted transformer achieves performance similar to that of DEIT small yet with only 50% parameters. Now let's see some details about why our shunted transformer is so powerful. The self-attention can effectively model long-range dependencies of the tokens and progressively expand sizes of their receptive fields via aggregating information from other tokens, while Conva has small-size receptive field. However, the self-attention mechanism also brings the cost of expensive memory consumption that is quadratic with respect to the number of tokens. The number of tokens equals to the width multiply height of the feature maps. As shown in this figure, the number of tokens represent the computation costs and the size of the token represent the receptive field of a token. If we apply the self-attention in bit and some later architectures private and ours on the same size of feature maps, the computation cost in self-attention of bit is much more. Therefore the self-attention can only apply on relatively small size feature maps or less number of tokens. In practice, bit takes 16 times 16 downsampling projection which significantly reduce the number of tokens. However, such operation generate coarse-grained and single-scale feature maps, the incurred feature information loss. PVT computes self-attention at high-resolution features, 4x downsample at the first few layers like ResNet, and reduce the cost by merging tokens with spatial reduction on token. Nevertheless, these approaches tend to merge too many tokens within one self-attention layer, thereby resulting in a mixture of tokens from small objects and background noise. Therefore we design a shunted self-attention via multi-scale token aggregation which preserve the ability of capturing small objects, multiscale objects and reduce the computation costs. As shown in this figure, our method can capture large objects like the sofa with one token unlike several tokens in self-attention which reduce the computation cost, and for small objects, we can capture them like the light unlike PVT which ignore them. In this slides, we simply compare different self-attentions. First of all, the Navy self-attention in bit which have global view but due to the quadratic computation cost with respect to the feature map size. Therefore in practice bit only apply on small size feature maps. Recent work try to reduce the computation cost of naive self-attention and apply them on large size feature map. SWIN split the feature maps and applies local self-attention on large size feature maps within small regions. However, such operation makes SWIN need to stack several layers to achieve a global receptive field. PVT reduce the cost by merging tokens with spatial reduction. Specifically, PVT merge the tokens of key and value. Nevertheless, PVT tend to merge too many tokens within one self-attention layer, thereby resulting in a mixture of tokens from small objects and background noise. Our shunted self-attention conducts multi-scale token aggregation for obtaining key and value of various sizes, which help capture multiscale objects and reduce the computation cost. We also compare our backbone with others on other downstream tasks like detection and segmentation. We take different detection framework like mask RCNN and RetuneNet and various evaluation metrics like bounding box average precision, mask prevention. We outperform previous SOTA focal transformer on various evaluation metric with less parameters. For RetinaNet, we report the performance on small, middle large objects. Our method consistently improvements which show the ability of capturing multiscale objects in our method.